Hey guys, this is video 10.2. We're going to be talking about the basic gas laws today. Now I will say this video could be a little bit longer, so if you kind of get the gist of things and want to move ahead, feel free to pause it and then go back. I'm going to work out every single problem. So we're going to do 4, 5, 6, 7 problems in this video, so it could be a little bit longer because I'm working them out. I'll try to move a little bit faster as we get going along, but if you feel confident and you feel comfortable, feel free, like I said, to jump ahead and just check work out, and if you need the practice, by all means use it. Alright, so we're going to jump ahead and we're going to move on to page 5. So these are the basic gas laws. Now really, you're going to be given the last one that we're going to talk about today. That's actually in your reference table on table T. So go ahead and make sure you have a calculator for this video and make sure you have your reference table out, because I'm going to kind of point some things out to you guys and I want you to be able to know where it is, because you're going to be all on your own when you take your quiz and your test and that Regents exam. So make sure you are familiar with where things are. First, let's talk about the 4 measurable quantities that we're going to be kind of getting into the rest of this unit. We have volume, and note this should be something you guys know by now. We have done this. You guys did a lab. Remember the cube lab way back, one of the first ones we did this year? You proved that 1 milliliter equals a centimeter cubed. So that shouldn't be anything, groundbreaking to us. Those are the same thing. Pressure, all right, in terms of our variables, V for volume, capital V. Pressure is a capital P. Temperature is a capital T. Moles is N. Okay, it's a lowercase n. So those are our variables with it. Now, when it comes to STP, that you should be familiar with, that stands for standard temperature and pressure. So if we talk about standard pressure, those are the units that you should by now have written down in your reference table. That's 760 millimeters mercury or torr, the 101.3 kPa, and the 1 atm. For this unit, though, we want to get in the habit, guys, that standard temp, the value we're going to use. Okay, it could be either or. It could be 0 degrees Celsius, but we're going to have to use Kelvin, and we'll talk about why that is in a minute when we get to that formula. So standard temperature are those two values. Table T also has the conversion factor, or excuse me, the conversion formula to go between Celsius and Kelvin, so make sure you're aware of that. And then standard pressure, we're going to keep it in ATM. Now you may see some of these basic gas laws using other pressure units, and that's okay. We will want to use atmospheres later on, and we'll talk about when that is when we get to the ideal gas law. So I'm going to also write in the other ones that you could see here. You do not have to convert them unless the problem asks you to go to a specific pressure unit. So for now, it's fine using all of these, but like I said, when we get to the ideal gas law, because of a value we're going to use, we'll have to use ATM. But more on that later. All right, the first law we're going to talk about, and check out the videos, guys, that I put in the classroom and on my YouTube playlist, because there's some really cool videos showing these laws in action. Okay, so check those out. They'll be labeled and all that stuff. They're really, really cool. Boyle's law, P1V1 equals P2V2. So graph of P versus Y, P versus V. Here's what that graph would look like. So if we have pressure here, it doesn't really matter which axes they each go on, but it says that it varies inversely. Okay, so inversely means it's going to be the opposite. As one increases, the other one's going to decrease. So for Boyle's law, that's what our graph would look like. Okay, well, really, it's going to be more like... That's fine. So here's our example. This is where it becomes very important, guys, that you write down your variables. You're going to see me work every single problem writing all my variables down. You should too. So here we go. We got 1 liter of a gas at this pressure. So 1 liter of a gas at 1.2 atm is allowed to expand. So that's the key words you're going to, kind of phrases you're going to see. Allowed to, or changes to, or something like that. What that means, guys, is that these first ones, these are my initial conditions. These are my subscript 1s. Okay, so I'm going to write those both down. P1 equals 1.2 atm. V1 equals 1.0 liters. So again, it's very important that you can identify which variables go together in terms of the 1s and the 2s, and then which ones are which, so you can figure out what you're looking for. It's not super complex once you know all your variables. It's just solving for an unknown variable. But if you don't know and recognize the terms as to which one pairs up with which, that's where things can get wrong. As always, show as much work as possible, because on quizzes I can give as much partial credit as possible if you show me work. All right, now it says allowed to expand, so that means everything after this is your secondary conditions. So we have a V2, which is 5.0 liters. What's the new pressure? So we're looking for P2. Now, as always, as I've done all year long, guys, I always solve for my unknown first. I encourage you to do that as well, but if you feel comfortable plugging in numbers and doing it, just show all your work. So P1 V1 equals P2 V2. I'm going to get P2 by itself, so I need to divide by V2. Those are gone. Okay, so my new formula is going to be P2 equals P1 V1 all over V2. Okay, so now I can plug and chug. 1.2 ATM times my first volume, which is 1.0 liters, all over 5.0 liters. Liters are going to cancel out. So when I look at this, my new pressure, now you don't have to worry about sig figs unless they ask you, but I'm going to put it in sig figs just as good practice. You should have 2, so 0.24 ATM is what my answer would be. Okay, pretty straightforward. Again, the hardest part is identifying your units and what variables you have. So I would encourage you guys, pause it, try this problem on your own, and then we'll talk about Charles' law. All right, so here we go. Sample of gas has a volume of 150 milliliters when its pressure is that. So that means these two go together. Okay, that I'm going to call my P1 is 720 millimeters mercury. V1 equals 150 milliliters. And then my new pressure is going to be increased. P2 is 750, and V2 equals blank. Now, one thing, guys, I didn't go back to in the example, but does my answer make sense? Well, what happened to my volumes? Volume went up, so what should pressure do? Since this is an inverse relationship, pressure should go down. So that's kind of a quick check that I know that I did it correctly and I'm on the right track. So here, if I take a look at this one, even before I solve it, pressure's going up, so what should happen to volume? Volume should go down if pressure's going up. So P1 V1 equals P2 V2. I'm looking for V2, so divide by P2. So V2 equals P1 V1 all over P2. Now it's just plug and chug. So 720 millimeters mercury multiplied by 150 milliliters all over 750 millimeters mercury. Those are going to cancel out. So when I look at this, my new volume is going to be about 140 milliliters. If you got 144, that is correct. Remember, I'm just rounding to correct sig figs. Just as a practice, you don't have to unless the problem asks you to. That's it, guys. That's Boyle's law. It's using those two variables. Let's continue on and talk about Charles' law. Very similar, except now we're going to be talking about volume and temperature. And notice what it says, guys. Volume varies directly with Kelvin temperature. So if we were going to draw a graph, it looks something like this: volume, temperature. As one goes up, the other one goes up as well. Okay, so again, thinking about it, does my answer make sense? If volume goes up, my temperature should go up, and vice versa. Now, one thing we have here is that temperature has to be in Kelvin, and this is going to be the thing that people get wrong most. Okay, they're going to forget to do this. So whenever you see a temperature right away, convert it to Kelvin. Use table T. You got the formula, plug in your calculator, write it down. Why? Why must it be in Kelvin? Think about this. Any ideas? Talk with a neighbor, maybe if somebody's right around you. Why does it have to be in Kelvin? What's unique about Kelvin? Well, if you think back, what's the coldest temperature we can have? The coldest temperature is possible, guys, is absolute zero. It's 0 on the Kelvin scale. That means that Kelvin can never be negative, and that's important here. Okay? Celsius can be negative. And since we're multiplying here with volume and temperature and dividing, can you ever have a negative volume? And the answer to that is no, you can't have a negative volume. That's why we have to use Kelvin, because Kelvin can't be negative, which means you won't ever get a negative volume. So where you might get problems wrong with this is if you don't convert to Kelvin. My encouragement to students is anytime you see a temperature, convert it right to Kelvin. It's going to be a good strategy, because formulas we use later on have to be in Kelvin as well. So just get in that habit right now. So here we go. We got a helium balloon that is filled with to a volume of 2.7 liters at 20 degrees Celsius. So V1 equals 2.75 liters. My first temperature, T1, 20 degrees. Now I want to add 273. That's my conversion factor, so that's going to be 293 Kelvin. Bam, done right away. I don't have to worry about it. The volume of the balloon decreases, so V2 is going to be 2.46 liters when it's placed outside on a cold day. What is the outside temperature? As I said before, guys, go check the videos out. There's a video for Charles' Law as well. It's a very cool video. I highly encourage you guys to see it because you're actually going to see liquid air. So this one is a little bit more complex to solve for than Boyle's Law, because now you have fractions. And if you don't get your unknown by itself first, guys, this is where you can get some common math errors, and I don't want that to happen to you. So look and see what I'm doing. First step when you have fractions, if you think about math class, clear the fractions. The easiest way to do that is to cross multiply. Okay, so now we get V1 T2 equals T1 V2. Okay, V1 T2 equals T1 V2. It gets confusing. This is why I encourage you to write everything down over here like I did. Solve for your unknown first, then plug in your numbers. If you plug in numbers first, I will guarantee you at some point you're going to mix things up and get it wrong. So I'm solving for T2, get it by itself, divide by V1. So T2 equals T1 V2 all over V1. Now plug in 293 Kelvin multiplied by my second volume, 2.46 liters, divided by my first volume, 2.75 liters. Liters are gone. Bam, now I can do the math. When I do that, you should get a temperature that is 262 Kelvin. Now think to yourself, did my answer make sense? What happened to my volume? Volume went down. Temperature should go down as well because this is a direct relationship. So if you feel comfortable, pause the video, try the U-try problem on page 6 on your own. Okay? So here we go. I got a volume, V1 equals 752. T1 is going to be 298 Kelvin when I add 273 to this. What's the volume? So I'm looking for V2. And T2 is going to be 50. So when I add 50 to 273, I get 323 Kelvin. So notice right away, temperature went up, my volume should go up. V1 over T1 equals V2 over T2. I'm going to cross multiply and clear my fractions. V1 T2 equals T1 V2. I'm solving for V2, so divide by T1. V2 equals V1 T2 all over T1. So V1 is 752 milliliters. Multiplied by my second temperature of 323 Kelvin. All over 298. Lost my train of thought there. So Kelvin cancels out. When I do the math, my final answer should be 815 milliliters. All right? So I'm going to, for the sake of the video so it doesn't get messed up, I'm going to pause this and I'm going to do part 2 in the next one. Okay? So I'll be coming back to finish Gay-Lussac's and the combined gas law.